Hello students, let us now take up a few questions from the chapter Conservation of Momentum, so to get ourselves comfortable with the topic. So today this question that we have is, a block of mass small m is placed on a triangular block of mass capital M, which in turn is placed on a horizontal smooth surface. So the surface on which this triangular block is kept is absolutely smooth, no frictional force at all. Find the velocity of the triangular block when the smaller block reaches the bottom end. Okay, so if all the surfaces are frictionless here, there is no friction between the block small m and the block capital M, and there is no friction between the block capital M and the ground. So no loss of energy anywhere, right? That's first thing. Second thing is, do we understand because of the gravitational pull the small block M will tend to come down? Now as it comes down, it will move along the inclined plane of the bigger block like this, right? Do we understand that this particular motion will have a vertical component downwards as well as a horizontal component rightwards? Now the block is moving because of gravity, which is acting purely in the vertically downward direction. Though there is a restriction to the block cannot move vertically down because it is kept on a inclined plane, right? But when it moves along the incline and it undergoes a horizontal displacement also, due to that, this horizontal displacement will, do you understand, will tend to shift the center of mass of this block and the bigger block system towards right. Now observe that there is no external horizontal force on the system. The only force acting on the system is in the vertical direction, the weight on the block M, small m. So can we say if there is no external force along the horizontal, F external along the x direction is 0, the center of mass of this system along the x direction cannot shift because initially the system was at rest. So the position of center of mass was a fixed position and it was not moving, and now since there is no force along the horizontal, the center of mass cannot shift horizontally, though it can shift vertically because there is an external vertical force mg. So if the center of mass cannot move horizontally, but the block small m is moving along the horizontal towards right, do you understand, to compensate for this rightward shift of the block, small block, the bigger block will have to shift to the left, right? So that as the block reaches down over here and acquires a certain displacement and a corresponding certain velocity also along the horizontal, the wedge or the bigger triangular block will compensate for that by moving towards left with a certain velocity, so that the center of mass of this system does not shift horizontally, it stays in its position along the horizontal. So now if we have to proceed with the mathematics of this question, let us assume that by the time the block small m reaches the bottom, it acquires a certain velocity. Now if we have to get that velocity, we have to first, let us take that velocity to be along the incline. If we say that, let's say the block has a velocity v along the incline, do you understand this v that we have written is actually the velocity of the block with respect to the triangular wedge? Why? Because understand that the triangular wedge is also moving towards left. Let's call this velocity to be v dash. So the block as it moves down, had the wedge been at rest, had the triangular wedge not been moving, the block would have simply moved along the incline down like this and it will have a velocity like this, right? So can we say if the wedge is also moving, the velocity of the block will change according to that? How will it change? Can we say this velocity that we have taken here along the incline then will be the direction of velocity of the block with respect to the wedge? Only when the wedge is at rest the block will move in this direction. If the wedge is also moving, then the velocity of the block will change because it is kept on the wedge. The effect of the wedge's velocity will come on the block also. How will it come on the block? Can we say that by definition the velocity of the block with respect to the wedge will be equal to the velocity of the block minus the velocity of the wedge? From relative velocity we know this, and from here then can we find out the value of velocity of block? Can we say velocity of block will be velocity of block with respect to the wedge plus the velocity of the wedge? That means if we want to find out the actual velocity of the block, the velocity of the block as seen from the ground, we need to add the velocity that the block has with respect to the wedge, that we have taken as v, with the velocity of the wedge itself, which we have taken as v dash. So, actually the real velocity of the block, the velocity of the block with respect to the ground will be the vector sum of v and v dash. Okay. For the sake of convenience here, maybe we can just work with the components here. We need not really find out the velocity of the block, at least not here. Maybe we can find it out later on. See that the first thing that we can use here to get the first equation, because we have two variables here, v and v dash, can we say that we can use the conservation of momentum along the x direction, because there is no force along the x direction on the system of the two blocks, that momentum will be conserved along the horizontal. What is the initial momentum of the system? Initially the system was at rest, so the initial momentum was 0. This should be equal to the momentum, the horizontal momentum of the block small m plus the horizontal momentum of the block capital M. Now, if we consider the rightward direction positive, understand that we can take the component of this v along the horizontal, and if this angle is given to be theta, we can see that this angle will also be theta, so that this component comes out to be v cos theta. So that the block's velocity component along the rightward direction with respect to the wedge is v cos theta. Can we say its actual velocity then, because we are saying that we need to take the vector sum of the velocity of the block and the wedge to get the actual velocity of the block. Along the horizontal, the block's velocity with respect to the wedge is v cos theta, whereas the wedge's velocity itself is v dash towards left. So, can we say when we try to add these two velocities horizontally, vectorially, we will get the velocity of the block m along the horizontal as v cos theta minus v dash. I hope all of you understand this. This is coming from the basic aspect that in order to get the total velocity of the block, we need to take the vector sum of the block's velocity with respect to the wedge and the wedge's velocity. And right now we are finding out that net velocity along the horizontal. So, velocity of the block with respect to the wedge plus the velocity of the wedge, right? This is what we are getting here. So, this is the momentum of the block small m along the horizontal, added to this the momentum of the wedge along the horizontal. So, can we say it is capital M, whereas the velocity of the wedge along the horizontal is minus of v dash. Why minus? Because v dash is in the leftward direction and we have taken rightward direction positive, right. So, can we now solve this equation to get the value of, or get a relation between v and v dash at least? Do we see we will get 0 is equal to mv cos theta minus m plus m into v dash, which will essentially give us v is equal to, let us get the value of v in terms of v dash, because ultimately we are supposed to find the value of v dash. In the question we are asked to find out v dash. So, let us get v in terms of v dash so that we can use it in the second equation. So, from here if you solve this, first thing is you will get mv cos theta, mv cos theta is equal to m plus m into v dash, and that gives us v is equal to m plus m v dash times small m cos theta, right. Let us call this equation as equation number 1, first relation between v and v dash. Now, how do we get the second relation? The second relation will come from the law of conservation of energy, because we know that all the surfaces are frictionless, there is no loss of energy anywhere, right. So, from conservation of energy principle, what do we get? What is the initial energy of the system? Do we see that initially the system is at rest completely, so no kinetic energy, whereas the block small m is kept at a height h. So, it has got a gravitational potential energy. How much? mgh, right. Whereas, when the block small m reaches down at the bottom, it loses all of its potential energy, and all that energy gets converted into the kinetic energy of the block small m as well as the block capital M. Mind you, taking the two blocks as a single system, it is the potential energy of small m which is giving the kinetic energy to both the blocks, to small m as well as to capital M, right. So, we will write the equation for conservation of energy as mgh, the initial potential energy of small m, is equal to the final kinetic energy of the two blocks. So, the wedge has a kinetic energy of half, capital M into V dash squared, whereas the kinetic energy of small m will be half m into what is the speed of small m now? Now, this is going to be another important expression here. See that we have taken the velocity of the block with respect to the wedge as v. This v has two components, one is v cos theta and the other will be the downward component v sin theta, right. And now we are saying that the actual speed of the block small m will be the vector sum of the velocity of the block as well as that of the wedge, right. So, can we do something? Can we take the components of these two velocities which are pointing in the same direction, add them together and then use our vector sum formula? So, see carefully in this figure that this v cos theta minus v dash is the net x direction velocity of the block, whereas this v sin theta is the y direction velocity of the block, right. So, Vx for the block is v cos theta minus v dash, whereas Vy for the block is v sin theta. And now, how can we find out the net speed of the block? Can we say the net speed v of the block will be nothing but Vx squared plus Vy squared whole square root? So, can we use this expression over here? Can we say that this will be v cos theta minus v dash whole squared plus v sin theta whole squared. This square root of that and then squaring it again, because we are supposed to write the expression half mv squared over here, right. So, this is what we will be left with. We can simplify this a little if we want to. We can just open up this bracket and get for this v squared cos squared theta plus v dash squared minus 2 v dash cos theta, and then this expression along with this will give us plus v squared sin squared theta. See that this term and this term can be taken together, and if we take v squared common, we will get cos squared theta plus sin squared theta, that is 1. So, the final expression here that we will be getting, I will just write it in the next expression now, mgh is equal to half capital M v dash squared plus half small m into, see that we are getting v squared over here from the two terms, v squared plus v dash squared minus 2v dash cos theta. This is what we are getting as the expression for the kinetic energy of the small block m, and this is the equation now that we are supposed to solve along with equation number 1 to get the value of v dash. So, the physics of the question gets over here. What remains now is the mathematics, because the two expressions themselves are a little complex, a little complicated. We have to work through these equations very carefully so that we do not make any careless mistakes while doing the calculations, and we need to get our answer for v dash. Okay. So, let us do that slowly and steadily and carefully. Okay. So, what we are going to do is, considering this as the equation number 2, we will substitute the value of v from equation number 1 everywhere in equation number 2, over here as well as over here, so that we get the whole equation in only one variable v dash, and then we will get the value of that. Okay. So, let us do it slowly and steadily. See that the first thing that we can do is this factor of half on the right hand side in both the terms, we can take it on to the other side, so that we get 2 mgh is equal to capital M v dash squared plus small m into, now inside the bracket wherever we have a v, let us substitute the value of v in terms of v dash there. Okay. So, that we have m plus m by m cos theta into v dash whole squared plus the second term is just v dash squared minus 2 times, once again we have a v, so minus of 2 times m plus m by m cos theta into v dash, and there is another v dash over here, right, this v dash. So, the two together will give us v dash squared and into cos theta, that is there in the last term. See that this cos theta and this cos theta will cancel out, right. And now what we can do is, we can take v dash squared common throughout these all the terms, here, here, here as well as here, everywhere we have a v dash squared which we can take out as a common factor now. Okay. And then we shall solve this taking LCMs and all to get our answers. So 2 mgh is equal to capital M plus small m into, let us take here an LCM also. We have an m squared cos squared theta down here, which we can take an LCM, which we can take as an LCM everywhere throughout this expression inside. So that we are left with m plus m whole squared in the first term plus v dash we are taking common everywhere. So okay, for now let me write v dash squared over here. We will take it a little in the second term first. So this plus, instead of v dash squared we will be now left with 1, and then since we have taken an LCM, we will have m squared cos squared theta left over here, isn't it? So this minus twice of, here we already have an m, so while we take the LCM we will just have m into cos squared theta. So m plus m into cos squared theta, and now this whole thing v dash squared has gone out, and now we have in the denominator over here m squared cos squared theta. See that one m here will cancel out with this outside m, so that we are left with m cos squared theta in the denominator, and now we can take it out and take an LCM over here in the first term also. So that we get 2 mgh is equal to capital M into small m cos squared theta. This is what we will get in the first term. Now I shall take this v dash squared and this v dash squared, all of them common together, right, so that we can have just one single expression in the bracket. So this plus, inside we will have m plus m whole squared plus m squared cos squared theta minus 2 capital M plus small m into small m cos squared theta, this whole expression now, and v dash squared outside. This is what we are getting as a common expression now, right? And now what we do is, the term that we have in the denominator, what is there in the denominator? M cos squared theta. Let us take this term onto the left side of the equation, so that we get 2 m squared gh cos theta on the left hand side, and on the right hand side now we will start working with the terms. So on the right hand side, see carefully that this term and this term, the first term and the third term, we can take an m cos squared theta out common, and we are left with capital M plus small m inside the bracket, right. So this is what we will get in the first and the third term together. The second term, let us keep as it is, m plus m whole squared, minus the last term also let us keep as it is, m plus m into m cos squared theta, and then let us take v dash squared down here. Now look at these two terms. This is m cos squared theta into m plus m. This is also m cos squared theta into m plus m, but with a 2, minus 2 rather. So minus 2 plus 1 will give us a minus 1. So writing the second term first, capital M plus small m whole squared minus the term that we are getting now as the sum of the first term and the third term will be minus of m plus m into small m cos squared theta, isn't it so? So this is what we are getting here after taking this term common now. And now let us close the bracket, and we are here v dash squared also we have, okay. So what are we getting now? Do we see that we can take a capital M plus small m once again common out of these two terms? Capital M plus small m, when we take out common, we will be left with, in the first term we have capital M plus small m left, minus small m into cos squared theta, isn't it so, into v dash squared. And now see this carefully, capital M plus small m into this, from these two terms we can take a small m common, so that we have 1 minus cos squared theta, which we can now write as sin squared theta, right, into v dash squared. and we are done. Now, all we need to do is take the expressions, this whole expression on the other side to get the value of v dash squared. So, see that we will get v dash squared is equal to 2m squared g h into cos theta whole divided by capital M plus small m into capital M plus small m sin squared theta. And now, this is the value of v dash squared. So, to get the value of v dash, all we need to do is take the square root on both the sides. So, that we get v dash is equal to square root of this whole term, and that is our final answer.